Hello everyone, you're welcome back to the fourth phase of the AI in Civil Engineering course. In the previous phase, we have worked with data, we've done data cleaning, we have done the feature engineering, and we did some exploratory data analysis. In the process, we created a new feature, which is the water to cement ratio. And now we will be going directly into building our first model. So I'm very excited about this because we have spent a lot of time, not more time, we've spent enough time on data engineering. Now we understand the data, but I also want you to understand how the model works. I will try my best and hopefully everyone will be happy about it. Okay, so first of all, you need to understand that a machine learning model is categorized into two. We have the classification problem and we have the regression problem. A classification problem is when you're trying to predict something that is discrete. For example, you want to know if the result is supposed to be A or B or C. For example, you're writing an exam, you want to know will you have A, B, C, D, or even F. So A, B, C, D, E, F. That's like a 6-class classification. It could be two kind of classification. For example, you want to know, is this a crack or not a crack? That is discrete. You cannot have anything outside that. It is discrete. Then when you're working on a regression problem is when you're trying to predict something that is a number. For example, in this case, we're trying to predict a number, which is the strength of the concrete. So we could predict 25.7 Newton per millimeter squared. We could predict 28.97. We could predict, something that is a number and that is continuous, it is continuous. So that is a regression problem. And because it's a regression problem, we need to use a regression model to solve a regression problem. And the baseline method for a regression model or a regression problem is linear regression. I want to, we have the clean data already. For example, if I come here, you remember we had this data. This was the original data that had 1,030 observations. Now that we have cleaned the new data, we have cleaned that data, I can simply just send this new one. This is how our new data looks like. It looks like this. I want to send this also as a CSV. So I can simply just say df to CSV, and then I will give it a name that I want. I can say this is clean underscore data, then I'll put the extension .csv. If I run this and then I come here, you can see now I have that data. So with this, I can easily just migrate to any of this notebook and then I run it as a CSV. I don't need to, work with it as if it's, that's quite better, all right? In order to understand the linear regression model, the first thing that I would like to do is that we work on the simple linear regression. So what we call a simple linear regression is just a linear regression with one feature. As you know, we have 8 features in total. 1, 2, 3, 4, 5, 6, 7, 8. We have 8 features. These are the inputs. So if I just put all of these 8 inputs into the model, you might have problems understanding how each feature interact with the model, because the model is like it's an hypothesis. We bring in the input and it gives us the output. Sometimes we will be unable to visualize the problem, because if you want to plot a graph, you can easily plot a 1D plot, which is a line, or a 2D plot, which is a plane, or you plot a 3D plot, that's a space, but it's like 3D, X, Y, Z. But when it goes to higher order, 4D, 5D, 6D, you cannot plot that. There is no 5D plot. There is no 4D plot. But because we have 8 input here, we have 8 input, for you to be able to see how all of them connect, you need a 8D plot, which does not actually exist, okay? So for the purpose of visualization, I'm simply just going to pick one feature and then we will work on it. We will not use a library. We will not use any machine learning library. We will just work on it by default by just writing the code. It's not going to be a long code. It's just going to be a very, simple and interactive code. Then when we understand that, we can then go to higher order and work with all of the 8 inputs at the same time. All right. So let's do that. I will close this and go to the part 2 model, which is specifically for model, building model. So in here, this is what we expect to see. the linear regression model, which I call the baseline model, we will have two parts. First, we have the univariate linear regression, which is one model, the simple linear regression. And then we go to the multiple linear regression, which is multivariate linear regression. And then, under the part one that we will begin right now, we will not be using any machine learning library. And then we'll use two methods. The first method will be the ordinary least square method. Actually, this is supposed to be least, not list per se. Okay, so we have the ordinary least square method. You will understand when we get there. Then we will also use gradient descent. So we will understand that as well. In this case, we will not use any machine learning library. But then when we are doing a multiple variable, which is all of the variables together, we will use this scikit-learn library because this will make our life much easier at that point in time. Okay, so let's just quickly dive into that. But then let's first of all understand the basics. So let's do the intuition. I will go to my whiteboard. Let's try to understand what a linear regression model is before we actually go into our real data, right? So say for example, I have this is my input, which I can simply call X, okay? It is my input. And this is my target, which is Y. Y is simply called target, okay? So say for example that the age of the concrete after 7 days is 15 Newton per millimeter squared. After 15 days is 31. After 19 days is 39. Then all of this. Then after 28 days, it is 57. So someone asked me and say, hey, Ridwan, what will be the strength of the concrete after 30 days? Or let's say after 33 days. You know, I can simply just pause and say, hey, I don't know, because we did not carry out the test for 33 days. The only thing we did was to carry out for 7, 15, 19, 20, 30, and 28. We did not carry out for 33. So how then are we going to obtain these results? Well, you can simply obtain these results by having a linear regression model. So if what we have is a linear relationship, if there is a linear relationship between the feature and the target, then you can simply have a linear regression model and you will predict what the strength at 33 days will be. Okay, so what is a linear regression model in simple terms? A linear regression model is a statistical model, or you can say a machine learning model, whereby we calculate some parameters and then we infuse this parameter in a linear equation, the normal linear equation that you know from the elementary mathematics or statistics. And then when we invite this into the linear equation, we can use this to make predictions of future target. All right. So say for example, now that the ones that I have, this is my measured value, this is my input, and then this is the target. These values here, they were measured on site, okay? They were measured from the lab. So I can simply just take this at 7:15. So I make this plot 7:15. This is where it crosses at 15 and 31. So I make all of these scatter plots. I can then have a linear regression model whereby I bring in my ruler and then I can draw this line, Ctrl Z. I want to make the line more thicker, so I'll pick maybe this. Oh no, that's too thick. Oh, let's do this. Okay. So I can simply just have a line that connects all of those scatter plots. Okay. So now this line is simply the model. It is simply the linear model, because this line is not just a regular line. It is a line that has some things we call parameters. Okay, so if you remember from elementary mathematics, the equation of a linear graph like this is usually written as y. Okay, now I need to change the ink. It's usually written as y equals to mx plus c, where y is the dependent variable. In this case, we call it the target. The target, what we're trying to predict. And then m is the slope of this linear curve. X is the input, okay? It is the input, and c is the intercept. So intercept is that point on the y-axis where this curve meets, okay? So that is what intercept is. But then in machine learning, we don't like to write it this way. Probably you don't want people to know that, hey, this is simply a linear curve equation. So we try to change the convention. So instead of calling this m, sometimes we call it beta 1, or we call it theta 1. And then instead of calling this c, we call it beta naught, or we call it theta naught. So you might find the equation that looks like this: y equals to beta naught plus beta 1x. Or you might see it this way: y equals to theta naught plus theta 1x. Well, it's still the same thing as y equals to mx plus c. So beta naught is the intercept, and then beta 1 is the slope in this case. Okay, so let's try to find out what the beta naught and what the beta 1 of this equation is. As you know, beta 1 is simply the slope, and slope is the y, the x. What you can call maybe y2 minus y1 over x2 minus x1. So how do I determine the slope? Well, it's quite easy. Let's change this ink to, let's say, maybe purple. So you can take an arbitrary position. So say, for example, I take a position here, okay, and then I map this. So the difference between this point and this point is the y, and the difference between this point and this point is the x. So if you do this, the y here could be maybe 57 minus 40 minus 39. That will give you the y, and then the x as well. You do a similar thing. So that would be 19 minus, that would be 30 minus 19. So eventually you will arrive at a value of 2. If you do this correctly, you arrive at a value of 2 for your B1. And then for B naught, as I said, B naught does not actually require much calculation. You simply just need to come here and see where does this line cross the y-axis. So this line at this position here, is just 1. So my B naught is 1. So if I transform this equation, I can transform this equation to be, let me use a different ink. So I can transform this equation to be y equals to, what is my beta naught? My beta naught is 1. Then plus, what is my beta 1? My beta 1 is 2. Then I simply put x. So I can say that this curve has a formula of y equals to 1 plus 2x. And this exactly is my linear regression model. As simple as that. Okay? So now you know what parameter is. Parameter simply means slope and intercept. Okay? So now let's go to the problem. The problem is to determine what the strength will be after 33 days. Okay? So you can simply, since you already have the equation of this model, all you just need to do is put in 33 in this case. So you have y equals to 1 plus 2, then you have 33, right? So 33 times 2, that will give 66. Then 66 plus 1, that will give 67. So the answer here will simply be 67. All right? So what we just did here is linear regression model. So in order to make prediction for something that maybe we don't have the target for, you can fit in a linear regression model on the parameters that you have the target for. The past ones, the one you have very certain of the results. You will build a linear regression model on that. And then you can use the parameters that you use for the ones that you are sure of to make predictions of what you want to make, what you want to predict. That's exactly what a linear regression model is. But then it's not usually as straightforward as this. This is just an example. Let's go to model 2 here. in the second tab, you will see that this model 2 is quite different from model 1, because with model 1, it was easy for me to draw a curve, a linear equation that connects all of the data points. But in here, it is impossible to draw a curve to fit in a model. That's the perfect way of saying it. So it is impossible to fit in a model that is able to connect all of the data points. So I can either decide to connect maybe this data point. Now this is what I did here. You see that I connected these data points, and this data point. 3 data points. So my linear equation was able to fit in on 3, and 1, 2, 3, they are left out. In here, I was only able to capture this and this. In here, I did not even capture anything. All right. So in reality, this is how models look like. In fact, this model I have here is still a simplified model. It is not a real life model. This is not how real data looks like. A real data looks like this. Like this. You would see how all of those dot points looks like. So it is very impossible to draw a linear equation that will capture all of these data points, because remember, a linear curve has to be straight, right? So you would see here, there is no way we can do that. So this is the problem of real life. But to not make everything complex, let's still go to what is not real life. Okay. So in here now, let's say we have this data. This is simply the data. At X, we have 19. At 15, we have 27, and all of this. Now we have fit in 3 different models. In this model, we have this curve. For this second one, we have this model, which is the red line. And for the third one, we have this green line. Okay. So this first one, I call it M2A. M2A, this first model. This second model, I call it M2B. And this third model, I call it M2C. Remember that these 3 models, they are trying to solve the same problem, which is this problem. I have X, blah, blah, blah. They are plotted with this. Now, my question now is that among all of these 3 models that you see on the screen, which one is the best? Which one is the best? Which one should you use for your calculation? You know, in the first model here, there was no concern of which one was the best, because the line simply connects all of those data points. It connects 1, 2, 3, 4, 5, 6. So there was no problem of which one is the best or which one is not the best. But in this case, it was impossible to have a line that connects all of those data points. So this connected only 3, this connected only 2, and this connected nothing. So the question now is, which of these is the best and which should you use for your model? All right. So it's not about the number of points you are actually able to connect, but how the accuracy will be if you want to make predictions. So how do we decide which one is best? Well, there's something that comes in place now. We call it residual, or maybe we call it error. And what is error? Well, let me check the ink. Okay, it's normal. Okay, so here, residual is simply the difference between the actual value and the predicted value. So say, for example, if the actual value is 19 here and you make predictions of 21, then the residual is 2. Okay, so let's see how this model behaves. Okay, so if you want to visualize this residual, the residual is simply the difference. You know, this is the measured value here, right? This position here is the measured value for this first data point, x1. This is second data point, x2, x3, x4, x5, and x6. So for this data point, x1, this is the measured value where you have the point. But according to the model is saying that this is where the true value should be. This is where the predicted value is. So the distance between here and here is our residual for this first data point, residual. And then here, there is no residual because the measured value is on the same line I'm talking about here. the measured value is on the same line as what the predicted value is. So the error here is 0. Here, the error here is 0 as well. But in here, there is an error because this is where the measured value is and this is where the predicted value is. Okay, so the difference between here and here, this is E1, E2, E3, this will be E4. Here, E5 is almost 0 as well. And then here we have E6. Okay, so you will do the same for all of these as well. You calculate the distance, which is the error between the measured value and the predicted value. So now we can do something. We have 3 different kind of error that I have highlighted here. There are several types of error. In the first one, we have something we call the ordinary error. We have another one we call the absolute error. And then we have another one we call the square error. Well, what I have written here in this first equation, let me call this equation 1. This is ordinary error. Then if I go to absolute error, well, absolute error is simply when I do the measured value minus the predicted value. Then I take the absolute, which means if this is -2, I will not record -2. I will say 2. That is what absolute means. Then the third one, so let this be equation 2. Then the third one, which is square of errors, let me say square of absolute error. This is simply y minus y hat, take the absolute and then square it. So this is the third type of error that we have here. Then you might be wondering, well, they are almost the same. Why do we have 3 different error here? Well, it's simply because of the usefulness of each one of them. So let's say, for example, the first one, which is the ordinary error. Now, your error could be positive and it could be negative. All right. So say, for example, this formula y minus y bar. For this equation to be positive, what you predict has to be lesser than what is the measured value. So say, for example, here, the predicted value is here and the measured value is here. So this will be a positive error. There is no error here. There's no error here. This, again, is a positive error. So let's say the difference between here and here is +2. The difference between here and here is +2 again. And then the difference between here and here is -2. So at the end of the day, when you do the summation of all of this error, you will have +2, +2, -2. Then at the end of the day, your error will simply be 2. So let's say for here, my error is simply 2. But then if I do absolute error, now absolute error here, 2, 2, then here I would not say -2. I would simply say 2 because I'm taking the absolute. Absolute value of -2 is 2. So in here, my error will be recorded as 6. And then square of error, I can simply just say 6 squared. So that will give me 36. Now, you would see that if you look at the magnitude of all of this error, it raises concern. If you are looking at the ordinary error, you might think, oh, you don't have so much error. But then when you look at the absolute error, you see that, oh, there is much error. And why is that? Simply because when you are using ordinary error, they can cancel out. See here, +2 can cancel out -2. But it does not mean that the error does not happen. Whether it is a positive error or it is a negative error, error is error. But ordinary error fails in that sense because it can simply cancel out all of those errors. Okay? So what we just did here, you can do the same thing for model M2B. You can do the same thing for model M2C. Then at the end of the day, you will look at which one has the least value. So say, for example, let's just do it simply. Let's say the error that we have here is 1, and what we have here is 7, and what we have here is 49. Then what we have here is 3, what we have here is, is 8, and then what we have here is 64. So if this is the case, we would simply have to judge that, okay, which of these error is the best? As I have said, which of this model is the best? Well, as I have said, ordinary error is not usually very useful anywhere. So you could use absolute error. If you take the absolute error, you see 6, 7, 8. Which of them is the least? Well, 6 is the least. So in that case, you will say this is the best error. This is the best model among these 3 models. So we are looking for the model that gives us the least error. All right. So, and then how do we get the model that gives us the least error? Because sometimes you wouldn't just know. You can't, how do you know? Okay. So to know that, we go to the next concept, which is called cost function. Okay. So a cost function, or let me say, cost function. Let's represent cost function with something we call, let me call L. Ctrl Z. I represent cost function with something called L. Then cost function could be based on any type of error. So in this case, we have 3 errors here, right? I have the ordinary error, I have the absolute error, and then I have the squared error. So let me use this squared error. So my cost function is simply y minus y prime, right? Then everything squared. I can rewrite this to be y minus y prime. What is y prime? Don't forget here, I wrote it in the first case here, that your y is simply b naught. So what we have here is actually y prime, which is predicted y, okay? So it's simply b naught plus b1x, okay? So in here, instead of writing y prime, I can substitute that into this equation and write b naught, let me put this in a bracket, b naught plus b1x, then I'll bring in this back, right, then squared. So my cost function is simply y minus maybe b naught, minus b naught, then minus b1x, then everything squared. Don't forget minus plus minus gives, minus times minus gives minus, then minus times plus also gives minus. So this equation is what we call the cost function. Now, remember that this equation is simply our error equation. I only just expanded it. So what I'm trying to point to you here is that if you look at this equation, you will see that this parameter here, L, which we call cost function, it is a function of what? It is a function of y. It is a function of what? B naught. It is a function of b1, and it is a function of x. Now, if you go further again, you realize that y here is the measured value. It is the measured value. It is simply what you have here. It is not something you have a control over. It is the measured value. It is the target. So it is not something you want to control. Also, x is the input value. You cannot control that as well. If I give you an input, you give me an output. It's not something you can control. The only parameters that we can control is b naught and b1. So we can reduce this to simply say that, well, this cost function is actually a function of what? Is a function of b naught and b1. Which simply means that if I want to reduce this cost function, I need to pick a value of b naught. I like to use different ink, but I know that slows me down. But to me, it just makes things look good. Okay, so for me to minimize this cost function, I need to pick a value of b naught and b1 that will help me to minimize this function. Okay, so in a linear regression model, what we are simply doing is that we are trying to, maybe sometimes we do a lot of iterations in order to get two things. We are trying to get what? We are trying to get b naught and we are trying to get b1. And the purpose of getting this b naught and b1 is that we cannot simply just pick a value of b naught and b1. Remember that your linear regression model is a function of b naught and b1, right? Because this is what your linear equation looks like. It is b naught plus b1. So without this b naught and b1, you don't have a linear equation, All right. So, but that B0 and B1, they need to be chosen systematically so that you can have the least cost function. All right. Then now the next question now will be, how then can we determine the best value for this B0 and B1 that will help us to minimize the cost function? Well, there are different methods. The basic one, which is the exact method, is called the ordinary least square error method. And then another one is the gradient descent method. So we will treat this one after the other. So now the first thing that we will do is that we will go to the ordinary least square error and see how ordinary least square error can help us to get the best value for B0 and get the best value for B1. All right. So see you in the next video.